Okay, thank you. So the first question, and so far the only question that have been posted on the sheet, is by Dr. Bhaskar Gupta. He is a faculty at, I understand, IIMT College, and he asks, how can introduce lab work in this subject? So we have started with electrostatics, and later on we will move on to magnetostatics, and these are pretty much theoretical area. Although there can be simple experiments designed on these topics, but I would rather request that you wait until the last module that we take up, that is induction of electric current. Then we change the electric flux, magnetic flux, and that gives rise to many interesting features. For example, when we have two coils, current flowing in one coil that induces some current in the other coil. It's called mutual induction, and an experiment can be designed, for example, for measuring the mutual inductance. That would be something really interesting. Then, if you have a coil that can carry a current, but you didn't attach any battery to it, you are just sliding a magnet, a bar magnet, through that coil. That will induce a current, and from that you can show explicitly how change in the magnetic flux induces a current into the circuit. And along this line, many other experiments can be designed. This kind of signal, electric signal that this kind of motions generate, that can be shown also explicitly in a cathode ray oscilloscope or a device like that. And that kind of experiments would be really interesting to design out of this topic. But that is mainly related to the motional electromotive force, the mutual inductance, or the self-inductance. That is the last module of this course. So from that part, very interesting experiments can be designed. From the other parts, it's difficult to design experiments because it's a theoretical development. For example, when we discuss the idea of electrostatic potential, the electric scalar potential, or the magnetic vector potential, and calculate them within certain boundary condition, there is hardly any experiment that you can design. Or if you can still design experiments for electric fields or magnetic fields. For example, if you consider a solenoid, if the solenoid is very long, that can be considered as infinite solenoid, then the magnetic field inside that solenoid, provided a fixed current is flowing through the surface of it, through the wire winding it, that would generate a constant magnetic field inside the solenoid and no magnetic field outside the solenoid. That can be shown using an experiment. That a nice experiment can be designed out of this principle. So we can maybe discuss about this if you are interested in a bit more details, and few interesting experiments can be designed out of these topics. But the topics towards the end will help more. I hope I have satisfactorily answered this question. If not, then you can write to me. I'll try to address the question in a better way. I don't see any other question posted yet. Okay, now there is another question from Pranjal. Problem 54, Introduction to Electrodynamics, Griffiths. So I understand Pranjal wants me to look up this problem 54 of the book. Just a moment, I'll have to bring out the book and see which problem this is. Can you write problem 54 of which chapter? Pranjal, can you write problem 54 of which chapter? That way I'll be able to address the problem better, I think. Maybe I move on to the next question. Arshi Rastogi asked, where should I practice vector calculus for better understanding of all these concepts? Vector calculus, the best book for practice, I would say, is by Spiegel, Vector Analysis. That's the book that if you go through the solved problems as well as if you try to solve the exercises given there, you learn a lot and you get a very good grasp on the vector calculus. I'm still waiting for Pranjal to write down which chapter he is talking about. Maybe we move on to the next question by Sejal. What is the actual meaning of permittivity of free space? Permittivity of free space, it just means that how electric field can propagate in that space, in free space. So as you know that when you bring in a source of electric field, if you bring in a source of electric field, you will have the electric field generated and it will take some time for that electric field to propagate from one place to the other. If you have the charge distribution changing, a fluctuating charge distribution, and if you measure the electric field from a distance, then it will take some time for that electric field to propagate from the source to the point where you are measuring. So you will register the change in that electric field after a time lag. So the permittivity of free space that determines how fast this information will propagate. In fact, as you know, any information can propagate not at a higher speed than that of light. So if you consider electromagnetic wave, that is light is a form of electromagnetic wave. And in case of free space, if you multiply the permittivity of the electric field and permeability for the magnetic field of free space, you get the square of the speed of light. So that's the idea of the permittivity of free space. I hope I answered this question properly. Then comes again the question of Pranjal, problem 54, electrostatics. Introduction to electrodynamics, Griffiths. Okay, let's see. Chapter electrostatics. Okay, the problem reads, imagine that new and extraordinarily precise measurements have revealed an error in Coulomb's law. The actual force of interaction between 2 point charges is found to be F equals 1 over 4 pi epsilon naught Q1 Q2 over R squared, 1 plus r over lambda times e power minus r over lambda r capped, where lambda is a new constant of nature. It has dimension of length, obviously, and it is a huge number, say half the radius of the known universe. So that the correction is small, which is why no one ever noticed the discrepancy before. You are charged with the task of reformulating electrostatics to accommodate the new discovery. Assume the principle of superposition still holds. What is the electric field of a charge distribution rho? Replacing equation 8. So, if your force is given like this, for 2-point charges, the force is given like this, then from this you can define the quantity electric field. If you have only one charge, so out of Q1, Q2, you get rid of one and make the other one, call the other one Q. That would be the electric field for a point charge. And when you know the electric field for a point charge, from that you can derive something equivalent to Gauss law for this context. When you derive something equivalent to Gauss law for this context, then you will be able to see the relationship between charge distribution, that is the volume charge density rho, and the electric field. And then you will be able to write down what is the electric field for a given charge distribution. There is also another way of doing it. You do it for a point charge. Now, if you consider a charge distribution, you can consider that by assembling very small charges into that space, and when you consider like that, you can integrate over that charge and then get the total electric field, and from that you can get the relationship between the charge distribution and the electric field. Then comes, does this electric field admit a scalar potential? A scalar potential is admitted when you have the curl of the field going to 0. That's the only requirement for a scalar potential being there. Because if you have gradient of curl, curl of a gradient, that will always go to 0. So the curl of that vector field has to be 0. Now you have this expression of the force, and from that you can trivially find the expression of electric field. You can calculate the curl of it, and if that goes to 0, then it will have a scalar potential. Then find the potential of a point charge Q, the analog of equation 26. If your answer to B was no, better go back and check it. That means answer to B is yes, which is quite obvious because the electric field would be only a function of R, and it's along R cap direction. It's not a function of theta or phi, so it won't have a curl. It's quite obvious by looking at this expression. And find the electric field, sorry, find the potential. So right from the definition of the potential, you can find the potential for this electric field. Then comes D, for a point charge Q at the origin, show that this identity is valid, where S is the surface, V is the volume of any sphere centered at Q. So Q is at the origin and it is surrounded by a sphere, and for that sphere on the surface and the volume, there is a surface integral in the first term, volume integral in the second term, and capital V in this volume integral is the potential. So then one is supposed to prove this, which once we have the expression for the electric field and the potential, this can be found out. Then comes E. Uh, Show that the result generalizes to when, so instead of a point charge at the origin, there is a charge distribution, and whatever charge is enclosed inside that volume, that is Q, E, and C. And this, again, this can be worked out considering a charge distribution, and we already know from A what is the relationship between the charge distribution and the electric field. Then comes F, draw the triangle diagram like figure 35 for this world, putting in all the appropriate formulas. Think of Poisson equation as the formula for rho in terms of V, and Gauss law, differential form, as the equation for rho in terms of E. Okay, so one needs to consider what is those relationships, and that has to be worked out. And then comes G, show that sum of the charge on a conductor distributes itself uniformly over the volume, with the remaining on the surface. Unlike Coulomb's law, well, where you had every charge going to the surface, here, for this kind of a force field, if you have a conductor, that will have some charge in the volume and the rest of it will go to the surface. That needs to be shown here, and that we can show by equating the force on the electrons or the quantum of charge inside the conductor going to zero. By making that go to zero, we can show that for this kind of a field, this would be the situation. If we consider a charged particle inside a conductor that is free to move outside the conductor up to the surface, then it has to be so that inside the conductor, under certain arrangement, it will have no force on it, and then it will be stable. And for this kind of a force field, that kind of situation will be satisfied. So you can show that in principle. So I hope I answered Pranjal's question. Then comes the question of Swapnil. How can we learn about the line, surface, and volume with geometric visualization? How can we learn about the line, surface, and volume with geometrical visualization? Line, surface, and volume are already geometrically visualized. I don't think I understood the question. Swapnil, if you can elaborate the question a bit, that would be better. In the meantime, I go for the next questions. The next question is by Gaurav. What are the demerits or failures of Gauss law? Well, the Gauss law doesn't have any demerit or failure as such. Gauss law is valid for all the situations. Anywhere electrostatics is relevant, Gauss law is valid. But if you want to determine the electric field using Gauss law, then comes the problem. Unless there is a symmetry in your charge distribution, unless there is a symmetry in the electric field, Gauss law is useless. It's true, it's correct, but you cannot find out the electric field from Gauss law. Because whenever we are using Gauss law, we are considering a surface that is enclosing the charge distribution, and we are integrating over that surface. We are integrating the electric field over that surface. When we are integrating the electric field over that surface, the normal direction to that surface, if that aligns along the electric field, then only we can find the magnitude of the electric field. If the normal to the surface doesn't align with the electric field, if there is an angle between them, then the dot product will bring in a cosine term, cosine between these two vectors, cosine of the angle between these two vectors. And if we don't know how much that angle is, In principle, we don't know that unless they are aligned. Then we won't be able to use the Gauss law to find out any electric field, any magnitude of the electric field. So as long as the normal, outward normal to the surface and the electric field, these are parallel or anti-parallel, we can find out the electric field magnitude using Gauss law, not otherwise. Therefore, symmetry is very important to find out electric field using Gauss law, but Gauss law is valid everywhere. I hope I answered Gaurav's question. Then comes a comment by Arshi. Also, I want to know how should I prepare electromagnetism for jam level. For jam level, electromagnetism, I guess in jam level, in addition to this course, you also have advanced stuff like electromagnetic waves, radiation, maybe a bit of relativity. I am not sure of the jam syllabus. If jam syllabus covers only this much up to the motional EMF, those parts, then going through this course and working out the problems of Griffiths, I think that would be sufficient. You won't need anything else. If you have more stuff in there, then that the other subsequent chapters of Griffiths has to be read, but I'm not sure of the JAM syllabus. So looking up, you may look up the JAM syllabus and prepare accordingly, I would say. Then comes the next question by Dr. Tyagarajan. Dr. Tyagarajan says, would you share the solution of assignment after due date? That will help us in main exam as well as check assignment mistakes. Yes, we do. So that is a common feature of NPTEL that we share the solutions to the assignments after the due date. Then comes a question from Aarti. What is physical meaning of susceptibility? So the English word susceptibility means how well the system responds to an external stimulus. Here in this context so far we have gone into electrostatics. In the context of electrostatics, it means how well the system responds to the externally applied electric field. Does the system develop a proportionate electric field that is very high or very low? If the proportionate electric field is very high, we say that the susceptibility is large. If it is low, then the material is not very susceptible to the external electric field. That is the meaning of susceptibility. I hope I answered this question. Then comes a question from Ruchi. In Griffith's electrodynamics, while talking about the boundary condition for reflection of electromagnetic waves in conductors, he says of ohmic conductors, there can be no free surface current as that would require an infinite electric field at the boundary of the surface current is zero. Please elaborate this. While talking about the boundary condition for reflection of electromagnetic waves in conductors. So, reflection of electromagnetic waves in conductors is not within the scope of this course. Anyway, if we consider, let me try to address this question anyhow. For ohmic conductors, there can be no free surface current as that would require an infinite electric field at the boundary. So if you have free surface current of an ohmic conductor, what is the situation? That means there is an electric field and the electric field is on the surface and the charge is getting transported on the surface. Whatever is the volume, whatever is happening in the volume, we don't care about that. So if you consider ohmic conductor, then its its resistance depends on the thickness. If you have no cross-sectional area, right, like the surface, which in principle doesn't have any cross-sectional area, then it will have infinite resistance. And if it has infinite resistance, you still have a free surface current that will require enormous, that is infinite amount of electric field. That's what Griffiths means in this context. I hope I answered this question. Then comes another question from Aarti. What is permeability? Permeability is related to magnetic field. It's so just like in propagation of information related to electric field, if you make a change in the current, then from a distance you will be able to measure the magnetic field, and the propagation of that information will take some time. So the medium or the free space, whatever is there, that is allowing this passage of information, that feature is permeability. Then comes the question of Swapnil. I want to ask, how can we learn the line, surface and volume integrals with geometrical visualization? I want to imagine the integral in my mind and then put the math on paper. No, just follow the question mathematically. Okay. Now I think I understand Swapnil's question. So you can visualize line, surface, and volume in geometry. And when you visualize line, surface, and volume in geometry, then the line integral, surface integral, and volume integral, visualizing them becomes easier. You consider some quantity, be it a scalar quantity or a vector quantity, and then you perform this integral of that quantity on this line, surface, and volume. So, for example, if you move one object from one place to another place, in that kind of a situation, you are moving it along a line. When you are moving it along a line, then the work done on that object is the line integral of the force that you are applying on it. So that is line integral, that is the geometric visualization of a line integral. When you are trying to calculate the flux of a field, then similarly the flux is over an area, so you require a surface integral. When you want to find out the total charge of a charge distribution, a volume charge distribution for example, you would like to integrate that charge distribution function over that volume. So these things are quite intuitive, this line integral, surface integral, and volume integral. You can geometrically visualize it with the examples that I suggested. Maybe that helps you. I hope I answered this question. Then comes the question of Ruchi. Please explain what is phase velocity and group velocity. Especially this sentence from Griffiths, because waves of different frequency travel at a different speed. It is in a dispersive medium, a waveform that incorporates a range of frequency will change shape as it propagates. A sharply peak wave typically flattens out. What does it mean by sharply peak wave will flatten out? Okay, I don't know which page of Griffiths this is, in which context of this is written. I can address the first part of the question directly. Phase velocity is omega over k. Omega is the angular frequency of a wave, and k is the wave vector or wave number. So omega over k is the phase velocity, which tells you the speed of the wave, that is the phase velocity of the wave. And if the wave is related to propagation of some particle or some physical quantity like energy, then the speed at which that particle or the energy propagates is d omega dk. That is the group velocity. For example, consider a quantum particle, an electron. It has a wave nature. It will have a wave packet, and that wave packet can be made by linear superposition of many plane waves. Now, if you pick up one plane wave out of it and take omega over k, that will give you the phase velocity, which may be more than the velocity of light. But that doesn't correspond to anything physical. Any information is not propagating at that velocity. So there is nothing to worry about. The group velocity is the velocity of that electron, that is the velocity of that entire wave packet, which is d omega dk. There is a big distribution of the components that summing over all that makes your entire wave profile. And that profile moves at that velocity, that is group velocity d omega dk. And when you have d omega dk, that directly corresponds to the speed of the particle in the context of wave particle duality, or the speed at which energy propagates throughout the wave, even valid for classical waves. um, you did not yet write which page of Griffiths says this statement, so I don't know the context of this statement. It would be difficult to comment on that. I'll wait for you writing the page number at least. By that time, let's move on to Lakshmi's question. Is there an internship opportunity for BSc students? Okay, this summer I'm not offering any internship because of COVID. It's difficult for someone to come here, and I don't think it would be a good idea to offer online internships. So this time I'll try to avoid doing that. Next question is by Azharuddin Muhammad. Gauss law simple explanation. So Gauss law connects the charge distribution to the electric field, or for any inverse square law, there can be an equivalent of Gauss law. For example, if you consider gravitational field, there also you can find an equivalent of Gauss law. Any inverse square central force will have an equivalent of Gauss law valid. So here we have calculated the divergence of electric field that we have found from Coulomb's law. And when we calculate the divergence of electric field, that is the differential form of Gauss law. So the differential form of Gauss law clearly tells us that if we have a point charge, then there is a problem. So the way Coulomb's law is designed, if we consider a point charge in the system, then we find that the divergence has a singularity at the point charge, at the point where the charge is located. Elsewhere, the divergence goes to zero. So then by using the integral form of the divergence theorem, we reconciled it and we got this Dirac delta function. But if we have a continuous charge distribution, then Gauss law nicely corresponds to that continuous volume charge distribution and the electric field. So again, integral form of that can be found out by using divergence theorem. So that's about Gauss law. I hope that answers Azharuddin's question. Is there any other question? I don't see any other question right now. Ruchi says, okay, there is another question. Ruchi says, thank you for clarifying. The line is from page number 418, chapter 9, EM waves. Let's see. The context is frequency dependent permittivity 943. Because waves of different frequency travel at different speed in a dispersive medium, a waveform that incorporates a range of frequencies will change shape as it propagates. Okay, so it says that if you have different components in a group of waves in a dispersive medium, so because it comprises different frequencies, each frequency has a different speed in that medium, so the shape of that wave packet will change as you move along. If you had a very sharp peak at one point in that wave profile, then after a while, after it propagated through that medium, because different frequencies traveled at different speed, it would flatten out. That's the idea. Now I hope your question got answered. Then comes the question of Gaurav. How does electromagnetic theory discard higher speeds than that of light? In electromagnetic theory, when you study the electromagnetic waves, which is outside the scope of our course, anyway, I'll answer this question. When you study electromagnetic wave, you can clearly see that the speed in free space at which the electromagnetic wave can move is that of light. That means square root of epsilon naught times mu naught, square root of the product of free space permittivity times free space permeability, and that is the maximum speed that it has. So by working out the Maxwell's equations, from Maxwell's equations you get the wave equation for electromagnetic wave. Light is a manifestation of that. It's just one type of electromagnetic wave. You can see that from Maxwell's equations, this is the maximum speed. It doesn't really discard higher speeds. It tells that this is the speed at which light will move or any other electromagnetic wave will travel in free space. I hope that answers your question. So Maxwell's equations are the one that does it, that clarifies on this. Then comes the question by Anudeep. Is it feasible to put antenna arrays in place of pantograph collectors to power them remotely by a generation station of X-band magnetron by IoT control Answer physiologic. I don't think I understood your question. This is clearly outside the scope of this course, and it talks about antenna, some powering those antenna, and IoT. I understand Internet of Things. So this is outside the scope of this course clearly, and I don't think I will be able to answer this question anyhow. Okay, then comes Azharuddin Muhammad. He says quantum entanglement. Quantum entanglement is something very different from electromagnetic waves, certainly. Quantum entanglement is, there is no classical analog. If you consider a many body state, it is more than the product of single particle states. And what more is the quantum entanglement? So I don't think without entering into rigorous quantum mechanics, I would be able to answer quantum entanglement. So I would rather like to avoid this question. Anyhow, this is not in the scope of this course. Then Arti asks, what is shielding in conductors? Shielding means if you have a conductor, then there is no electric field inside that conductor. So if you want to shield some area, that means protect some area from external electric field, you can surround that area by some conductor. So the electric field won't be able to enter that region because it's surrounded by conductors, and at the conductor the electric field has to be zero. And then if you look into the potential, the electrostatic potential, and the solution to Laplace equation, that will tell you that if everywhere on the boundary the potential has to be zero, and the potential cannot have any maximum or minimum inside a charge-free region, you will see that inside that region also there would be no electric field from that Laplace equation conditions. Therefore, you can shield a region in space from electric field by surrounding that region using conductors. You have possibly noticed that when you are talking over your mobile phone inside a lift, which is made of metal, there is no glass, then it's very difficult to have that connection going on because mobile network is electromagnetic wave, and when your phone is completely surrounded by metal conductor, you hardly get any signal from the mobile towers to your phone, to your device. So your phone is shielded in that sense. But if you have some glass in the elevator, then this doesn't work because glass is transparent to electric field, while the metal is opaque. I hope this answered you. Then comes Sarita's question. Is there possible of a single electron to have wave velocity? Single electron can have a velocity as long as it's moving, and that single electron can be represented using a wave. So in that sense, yes, it has wave velocity. If you mean something like if a single electron can go up to the velocity of light, no, not up to the velocity of light. There is nothing apart from light or electromagnetic wave that can attain the velocity of light. It would be slower, but how slower? It can easily go up to half the speed of light, a single electron. And it can be accelerated even further. Half the speed of light is not very unnatural. Even if you look at the core electrons in gold, they move at half c, that kind of a speed. So that is seen in many cases. There are even heavier atoms than gold. The speed even increases further. Azharuddin wrote Mainster effect displacement current. That's not really a question. Can you please form a question and write, that would be better, I think. I didn't understand what I should tell when you write this. I am waiting for more questions. I can tell you that displacement current would be covered towards the end of this course. If you want to learn more about displacement current, so you can move along with the course and you will learn about it. I don't see any other question. Okay. Anlin wrote, how does microwave travel through a magnetodielectric medium? Microwave is just an electromagnetic wave of micron wavelength, and magnetodielectric medium. What is that? The medium is magnetic as well as dielectric, is it? So if it is dielectric, then electric field can pass through very easily. There is no problem. And magnetic material doesn't quite shield magnetic field. It's the conductor that shields electric field. So if you want to block an electromagnetic wave, you shield the electric field, and only the magnetic field cannot make an electromagnetic wave propagate. That's how you do it. There are also metal parts in a microwave oven that you see in your household appliance, and there are holes inside that on that sheet, metal sheet. So when there are holes on that metal sheet, depending on the diameter of that hole, it may be transparent or opaque to that microwave. The microwave wavelength is of micron length. If the whole diameter is smaller than micron length, then it will understand that it's just a continuous conductor. It won't be able to propagate through that medium. But if the whole diameter is larger than a micron, much larger than a micron, then it will understand that it at places it will see the hole and it will propagate through that shield a bit. Then comes a question from Azharuddin. Explain the supercooled conductors. Supercooled conductors, do you mean superconductors at very low temperature? Superconductivity is something completely different, a phenomenon where electrons don't find any resistance whatsoever in moving through that material. And this is a strongly correlated electronic phase. It has hardly anything to do with electromagnetism. It doesn't depend on what is the amount of electric field you apply. It depends on the coherence between the quantum state of those electrons that participate in superconductivity. Then comes a question of Dibakar. This is out of the course question. Please explain what is absorption spectrum. Absorption spectrum is there are materials that absorb in certain range of frequency, that is wavelength. So, and some other range of frequency, that is wavelength, is not absorbed. It gets either reflected or transmitted through that material. So absorption spectrum means you can, by shining light of different wavelengths or shining any other form of electromagnetic wave of varying wavelength, you can find out at which region of frequency the material absorbs the electromagnetic wave and in which region it doesn't absorb. So where it will absorb, that means the absorption is associated with some electronic transition from some ground state to excited state, and the energy difference between these two states, that is the ground state and excited state, that has to match this frequency of the incoming photon. That means you can find out where are the ground states and excited states located, how much is the gap between them, and what kind of physics is there in that material. That's what you find using an absorption spectrum. Then there is a question from Mani. What is mean Poynting vector and boundary condition? Poynting vector, again outside the scope of this course, Poynting vector is a cross product of the magnetic and the electric field that tells you in which direction the energy associated to the electromagnetic wave will propagate. That means the direction of propagation of an electromagnetic field. And boundary condition, so you have boundary condition on the electric as well as magnetic field. The cross product will have a certain set of boundary condition as a consequence of the boundary conditions that you already know for electric and magnetic field. That's about it. Then comes a question from Nachiket. If I place a flat metal sheet in front of a charge, this will polarize the sheet. Now, what if I ground the other side opposite to the charge of the plate? Will that shield the space opposite to the charge? Okay, if you have a point charge or a distribution of charge in front of a metal sheet, then that metal sheet will get some induced charge for sure. If you ground that metal sheet, you cannot ground the opposite side only of the metal sheet. If you are connecting a conductor to another conductor, then the entire conductor is connected to it. It's not one side that gets connected and the other side remains like that. If you ground it, that means you are bringing that entire sheet to zero potential. Ground is zero potential. There is no electrostatic potential in the ground. That's our reference of electrostatic potential. So as soon as you are grounding that sheet, you are bringing the entire sheet to zero potential. But zero potential doesn't tell you anything about the charge distribution. The charge distribution can still be there. And of course, if you have this constraint of having the entire sheet at zero potential, of course, the charge distribution will change, but the charge distribution will remain there in such a way that the potential throughout that sheet remains zero, subject to the electric field arising from the charge distribution that is elsewhere, the charge in front of which you brought this conductor, brought this metal sheet. So the entire charge distribution will not go away. The charge distribution will reorganize itself in such a way that the potential becomes zero on the plate. Okay, there is another question by Anlin. What happens to EM waves when it passes through a multi-layer material with different dielectric constants? With different dielectric constants means it has different refraction indices. So it gets refracted, it has different velocity through different media, and if the angle of incidence is not normal, if the angle of transmission is also not normal, then the light bends. The electromagnetic wave that doesn't travel in its original direction, its direction shifts as a result of the refraction. Different dielectric constant means different refractive index as well. I hope that answered your question, Anlin. I don't see more questions. You can write more questions if you wish. Yeah. Okay, great. Thank you. So that's all for today. Let's meet you in the next live session whenever we organize it. Bye for now.